Hello, everyone. This is a regular secret seminar. It is our pleasure to have Professor Ma from Peking University. Today, he will talk about Lorentz violation of cosmic photons and neutrinos. Yeah, please.
Yeah, thank you very much. And also, I'm very grateful to Professor Park for the invitation. Today, I would like to introduce some of the works of my group on cosmic photon and neutrino on their relationship with Lorentz invariance violation. So the contents of talk is from the collaboration work with a number of my students, and some of them are undergraduate students during their work. We know that the highest energy particles can be observed by human beings from the sky. So this is a frontier of human knowledge in cosmology, astronomy, and physics, and is a combination of those fields leading to a new direction we will call cosmology and the particle astrophysics. So it's give us a chance for a better understanding of the universe from the small to the most big, connecting quarks to the cosmos. And also here we have a chance to learn some new physics from cosmic photons and neutrinos, such as Lorentz violation and CPT violation. We know that the special relativity has been with us for over 100 years. And there are two basic principles, one by special relativity. The first principle is principle of relativity, means the equation describing the law of physics have the same form in all admissible frame of reference. Another principle is the principle of constant light speed. It means that the speed of light is the same in all directions in vacuum, in all reference frames, regardless whether the source of light is moving or not. So we know that relativity has been very successful and become one of the foundations of modern physics, and has also proved to be valid at very high precision. So the Lorentz invariance is a basic theoretical foundation of relativity, states that equations describing the law of physics have the same form in all admissible reference frames. So is there any reason that we still seek for Lorentz violation? The reason is related with Planck. Before the establishment of his theory on black body, Planck thought about the unit system. He called the God-given system of the human being, or any civilized special, not only human being, but other civilized cultures. He used the basic constants to organize the basic units. And from there, we know that he actually, in his work, he introduced the constant, and later on was found to be the basic constant in quantum mechanics. We called Planck constant. So use the basic constant of the velocity of light, gravitational coupling constants, and the Planck constant, we can establish the length units, time units, and energy units. And it's thought by most people that at this energy scale, our space-time might be discrete, not continuous. So this can give rise to the quantum gravity. So Lorentz violation can serve as a window to study the nature of space-time, to study such the quantum gravity effect. From history, we know that many early discussions on the efforts of Lorentz violation, for example, Dirac's new ether theory, and also some spontaneous symmetry breaking, and universal length scale, and also other kinds of work. And at the moment, there are many possible ways for Lorentz relation from different theories. For example, one is a space-time form theory from string theory. Another one is loop quantum gravity. Also, the backgrounds in general relativity can give rise to the Lorentz violation, and also the spontaneous symmetry breaking of vacuum. And also they are doubly spatial related, even from geometry. For example, Finsler geometry can give also the chance to study Lorentz violation. So one of the most common one is that we can use the standard model framework of the field theory, use the languaging, and we can add Lorentz violation terms to this languaging and study the Lorentz effect, violation effect also. So this kind of work called the standard model extension. It's from the particle field theory framework. So many theories predict new physics beyond conventional knowledge. So which one is correct? We know that physics is an experimental science. So any theory should be tested by experiments. So if we try to find the Lorentz violation, the effect is too tiny to be detected on the Earth. So we should look up at the sky again. We can use ultra-high energy cosmic rays, cosmic photons from gamma ray bursts, or cosmic neutrinos with much high energy to study, for the chance to study Lorentz violation. So one of the astrophysical process we can study Lorentz violation was pointed by a group of people 20 years ago to use gamma ray burst. And we know that gamma ray burst is the most energetic astrophysical process except the Big Bang. So, this source with the emission of both low energy photons and high energy photons. So we can check the arrival time of low and high energy photons, the time difference, to check whether there could be something related with Lorentz violation. And also the gamma ray burst, they have usually two types. One is long gamma ray burst with duration time larger than 2 seconds. Another one is short gamma ray burst with duration time less than 2 seconds. And the long gamma ray burst is with very long distance, is several billion light years from the Earth. So the redshift is usually around 2. But for short gamma ray burst, it's near the Earth, still 2 billion light years. The redshift is the average redshift for short gamma ray burst is 0.5. So we use the modified photon dispersion relations, which means that the velocity of light is energy dependent. So usually we have two terms. One is the linear dependent, is a quadratic energy dependent. So usually we can study, and we think that the scale of the suppression should be of the Planck scale. So if the suppression scale is approaching the Planck scale, we think it's a reasonable scale to reflect the Lorentz violation of quantum gravity. And the picture is very simple. For example, we suppose at the gamma ray burst, at the time it have emission of 2 photons. One is a low energy photon, another is high energy photon. And if the travel velocity of these two photons have energy dependence, for example, if low energy photons travel faster than high energy photons, so the low energy photons can arrive us earlier at the detector, and later on we can detect high energy photons. So that's a rough picture about the idea we check for energy dependence of light velocity. And the data we analyze is from the Fermi satellite by NASA. So the Fermi satellite was, they have two detectors. The GBM detector, they use detector photons with energy of keV or MeV scale. And another detector is light. It can detect photons with energy of several GeV to 300 GeV by maximum. So we from here, so the two detectors they combine together. We can measure the arrival time of low energy photons and also high energy photons, and check their energy, their arrival time difference. So that's the data we can use. And in our study, we make assumption that the dispersion relation of the photon, that's energy, that moment, S means S equals positive means subluminal, means the light speed is less, the high energy light speed is less than the low energy one. And S equals negative means superluminal case. And for the power, we usually use N equals 1 corresponding to the linear energy dependence, and N equals 2 to the quadratic energy dependence. So in our fitting, we usually choose one case, and in most of our choice, we use N equals 1 in our study. That's one of the light curve by the short gamma ray burst. It means 2009 on May 10th. So that's a gamma ray burst. And the curve, the horizontal axis is the time, arrival time. And the above, the green figures mean low energy photons. And the lowest one means the arrival time of high energy photons. And from here, we notice that high energy photons arrive slightly later than low energy photons. So it means that high energy photon arrived earlier than arrived later than low energy photons. So this gives the time difference between low energy photons and high energy photons. From there, we can make estimation whether it's a right scale for Lorentz violation study. And previously, people make estimation, make assumption that the emission time of high energy photons should during the arrival time of low energy photons. And with this assumption, people arrive at very big constraint. For example, it's about 6 times of Planck scale. So it's a simple assumption that the emission time of high energy photons is within is during the low energy emission stage. So that was the first impression. So from here, we notice that the scale is around the Planck scale. So it means that the time is mature for us to study the Lorentz violation from the arrival difference of low energy photons and high energy photons from gamma ray burst. And in the last more than 10 years, our group made detailed study on the Lorentz violation from energetic photons of gamma ray burst from the analysis of Fermi satellite data of light curves from gamma ray burst. and also from AGN. So the formula in our analysis, we use the velocity for the linear case and for the quadratic case, and we use ELV as a parameter to fit the data to see the scale, whether it's reasonable or not. And because the long distance from the source and our detector, so the gamma rays emitted by gamma burst should have we should also consider the cosmic propagation effect due to the expansion of the universe. So this time lag difference for high energy photon and low energy photon, that's the energy of high energy photon, that's the energy of the low energy photon. So if they were emitted at the source at the same time, so their speed difference can be calculated to cause the energy difference purely by Lorentz invariance effect. So from here, we notice that the cosmological factors, the expansion universe and acceleration of the universe, all the effect has been considered. And just recently, we have a new derivation of this formula, exactly same from a Fensler geometry. Means that Fensler geometry could be also a way to start Lorentz violation for particles propagation in the universe. So this another gamma ray burst. The lead curve is 2008, sometime power 16. So the above figures means the lead curves of low energy photon. The lowest one, the last one means it's a high energy photon for photons with energy larger than 1 GeV. This is another one we just showed. Here it has a high energy photon with energy of 31 GeV. So this is one of the highest photon observed by this gamma ray burst. And about 10 years ago, around 2010, at that time, we tried to study the Lorentz violations, try to check the arrival time difference between high energy photon. So first, we check photons with energy larger than 10 eV. At that time, there was only 4 events. So that's the energy of these 4 events from different gamma ray bursts with different red shifts. So that's the observed time between the high energy photon detection time and the trigger time of the gamma ray burst. So if we just make assumption, the observed time difference is equal to the time difference due to Lorentz violation. So that's the time scale we got. And from here, we are encouraged to see that the scale for the linear dependence just corresponding to Planck scale. But if we make assumption that the observed time difference just due to Lorentz violation, so from these 4 events, we have we calculate the Lorentz violation scale for linear case. It's with center value, but with very large error. So from here, we can say nothing about the Lorentz violation. But we know that the emission of high energy photons and low energy photons might be at a different time at the source, because we don't have enough knowledge about the radiation mechanism of the gamma ray burst. So one of the way is that we make a separation of astrophysical time lag from Lorentz violation delay. So in this way, we can introduce an intrinsic time difference between low energy photons and high energy photons at the source. So this delta T in means the intrinsic time difference between the high energy photons and low energy photons. So this means that the low energy photon and high energy photon were not emitted at the same time at the source. So the observed time difference is due to the combination of Lorentz violation effect and the intrinsic time difference. And from this equation, we can make further analysis. We code the this observed time. We can use tau, and the k we can use kappa. So we can use tau kappa plot to make analysis. So that's a way we make analysis. If the events fall on a straight line, inclining line, it means that it has related with the Lorentz violation. And from the slope is 1 versus the ELV. So from the slope, we can make extraction of the Lorentz violation scale. So we are encouraged to see in this paper, use this method, which we found that 3 events from long gamma ray burst fall exactly on same line. So just use this line, we can get the linear energy dependence of light speed with the ELV of this scale. So and we see that it's around the Planck scale. But if we use a quadratic energy dependence as input, for this case, we still have the linear dependence. The 3 long gamma ray bursts, the 3 events fall on the same line. But the energy scale is much short, much smaller than Planck scale. So it's not a reasonable scale to start the Lorentz violation effect. So from here, we cannot arrive at a very strong conclusion, but we just said that it might mean that the light speed might be a linear dependence with the correction of the scale around the Planck scale. So we restarted this problem 5 years later with more data available. So the Fermi-LIGHT, Fermi collaboration, the by light detection group, they released more data with photons with energy larger than 10 GeV. So it's around more than 10 new data. And this data are from the paper by Fermi-LIGHT, not collected by us. So we just put, so I suggest the students to draw these new events on the same plot we plot before. So that's a new plot. The 3 black events are previous events, and the other events are new one. And we are very encouraged to see 2 events from 2 long gamma ray bursts fall on the same line. But we still found it's not so regular. So at that time, we cannot draw very strong conclusion. And we did not observe that these 3 points can be considered along the same line as this line. At that time, we did not found that. And later on, another student involved in the study, at this time, he tried to think we should, because in our calculation, we should use a low energy photon as a benchmark to compare for the arrival time difference. So the arrival time difference of high energy photons should be compared with the low energy photon arrival time. So previously we used the trigger time as the arrival time of low energy photon. Then the students think that the trigger time is not a reasonable one because the gamma ray burst source are at a different distance, and also their flux are not the same at the source. So the trigger might be very sensitive to the brightness of the gamma burst and also to their distance. So he suggests that we choose the peak of low energy photons. So we should use the first significant peak of low energy curves. For here, for example, here we use this one, the first significant light curve of low energy photons as a benchmark of low energy photon. And so for this one, that's the position of the low energy curve. So we see that it's not very different from the trigger time, not very different, just a few seconds difference. So that's the arrival time of the high energy photon. That's a red shift, the gamma burst. That's a different gamma burst. That's the energy of the observed events. That's the energy of the photons at the source, because the red shifts. So the observed energy is not equal to the source energy of the photon. And then we draw our plots again. To our surprise, we found very good regularity of the high energy photon events. For example, for those events, we found that that's 8 events falls exactly on the same line. So if we take this line as a real regularity of high energy photons, so the slope of this line means that it's 1 versus ELV, the Lorentz violation scale. And the intercept of this curve with a vertical axis means that it's an intrinsic emission time of these photons. And also the events fall on same line means they were emitted at the source at the same time compared to the low energy photons. So we give a picture that high energy photons was emitted at the source earlier than the low energy photons, but they were, because they have a small velocity, so they need more time to arrive to the detector. So we will observe later than low energy photons. So that's a picture we got. And to our surprise, we just got this paper published, just finished the proofreading. And then we look at the Fermi data again. We found another gamma burst happened on 2016, May 9th. And it have events with the energy, high energy photon events around 52 GeV. And also we have the low energy light curve. We use the most significant one as the low energy arrival time. And then we draw this plot, these points on our plot. So that's detailed information of these events. Observed events is 52 GeV, but the emission energy at the source is 100 GeV. So we plot these events on our fig. To our surprise, these events fall exactly on the main line we suggested. So it's a surprise to us because the regularity is so good. So from here, we give the conclusion that this event is an evidence to support our prediction for linear form modification of light speed. So we were lucky to got the paper published very quickly because, yeah, just probably just 2 weeks after we submitted the paper, it was accepted.
Professor Ma?
Yeah.
Yeah, I have a
Can you hear me?
question. Yeah. So in previous plot,
Yeah, this
here.
one.
Yeah, can you explain again what the slope means and what's the interception mean?
Yeah, the slope means 1 versus ELV, the Lorentz violation scale.
Right.
1 versus.
Okay. Now
The
mhm.
intercept means the intrinsic time difference between high energy photons and low energy photons.
Okay. Now the question is, so for example, in the black line, there are several observations. Several different observations, right?
Yeah.
So why they have the same interception?
How to interpret?
Yeah.
There are several parallel lines. In every line, it means that the event was emitted at the source at the same time. Parallel means that each event on line means that they were emitted at the source at the same time. Parallel means that those events falls on different lines. They were emitted at the source at different time. Because the source is not emission of photons at the same time, it's continuous emission. So it's some events happen, and some minutes, some seconds later, other events also emitted.
Mm.
So the several parallel means that they were the events were emitted at the source with the same time on a straight line. So this means that the first 3 events emitted more earlier at the source, and later on its main line. So with 9 events, high energy photon events emitted, and later on there are also those 2 events have very low energy, just around 10 or 20.
Let me see. So you mean that in this new GRB 1605 something, you have all this kind of light was emitted from one object, or?
No, they are from different source.
Right.
But we use time at the source. This observed time divided by 1 plus redshift means that the time at the source.
Mm.
So that's a rescued time.
Mm.
So this rescued time means the time at the source. If there is no Lorentz violation, it means ELV equals to infinity. It means that the horizontal vertical line, horizontal line should be same time at the source. But if we have Lorentz violation effect, inclining line means the same time at the source.
Okay, I see. Okay, thank you.
Yeah. So from here, we just look at the lines by eye. We judge the results from just by naively seeing that. So to make our analysis more general, we use more general methods, just like something like maximum entropy method. And from here, we can have a complete scan over all possibility without bias. So that's a way, for example, that's the same event. So we make analysis, use this general methods, and we check ELV at different scale. And we found just at the conclusion at our scale, that's a very significant C of this red line. So that's a peak here. And the peak means it's 3 to 5 sigma significance of this signal. So for ELV equals the results we just obtained from drawing straight lines. So here is the general analysis method. And
sorry. So what is the vertical axis S in the left figure?
The left picture means we have a complete scan.
Yeah.
Of all ELV.
Yeah. So
the middle red color means it's the average. It's just the background.
Yeah. So my question is, what does the vertical axis mean in the left figure?
Oh, it's something like entropy, just the quantity to judge. It's not important. It's not important.
I see.
Just the curve, the regions with the color means 1 sigma, 3 sigma, 5 sigma within the background. So this this peak of the red curve means it's 5 sigma beyond background. It's a signal significance. So this general method, not by drawing a straight line here, not like this one. And we just check all possibility of lines to check the conclusion. So other way of drawing just compatible with background.
Right. But here, did you assume also linear?
We just make, for example, it's Monte Carlo. We make a change of the order of those events, make random change. So we draw this background events, background curves.
Right. So in the left picture, so did you assume?
Yeah, here we have definite data for one event, for example, kappa and tau time, and we make random change of this events and make its work. It can be those events are from just the data, and then we make random change of this to have the background.
Well, right, but did you consider still linear dispersion relation between free and energy?
Yeah, we just check whether it's have a regularity of the data or it can be randomly chosen. So for the randomly chosen results, our results should be within the red region, the yellow region, the green region, the dark green region. It's just means their background. But for this real events, we found this signature is beyond background. So it means that this is a very strong regulation. It's an indication of ELV equals to this value. So this from a general method. And just last year, we found several events, high energy events that arrival earlier than low energy photon events here from different gamma bursts, 3 events. So because in our picture, those high energy events were emitted at the source earlier than low energy photons, but they are observed after the low energy photons. So the intercept means the emission time of the low energy of high energy photons. But here we check that several high energy photon events just observed before the low energy photons. So our picture is further supported by these 3 events. So we think these three events provides direct evidence for pre-burst stage of gamma ray burst. We mean pre-burst means that at the gamma ray source, high energy photons were emitted earlier than low energy photons, around 10 seconds before the main low energy photons. So we call this the pre-burst of high energy photons of the gamma ray burst. And later on, we make another study from the machine learning methods. So that's events, the same events, gamma tau plots. And we have all events larger than 1 GeV. And then we use machine learning to make classification of the events into different classes. So the middle one is the one from our machine learning method. It means that the middle cluster belongs to one class of high energy events. And then we make analysis of this in our general methods, and we found a significant peak larger than 5 sigma. So this way, we also suggest support a pre-burst stage of gamma ray burst and support of light speed variation at ELV equals this value. So that's our study on the Fermi data of high energy photons larger than, with energy larger than 10 GeV, and also with known redshifts. And also we studied the AGN case, but for the AGN case, for the study of light speed is not so good because the distance usually near in the gamma ray burst. Another point is that the energy of the AGN photon events can be higher as TV scale. So it's still good to study the Lorentz violation effect. So if we just check some time difference between high energy arrival time and low energy arrival time, different bands, and we found that the scale is around the Planck scale. But we look more carefully. For example, for this AGN, they have very significant time arrival difference between the two energy bands. The first one, the first case, for the energy between 0.15, 0.25 TeV. The last one is for photon energy between 1.2 to 10 TeV. So that's arrival time difference. It is observed they have 4 minutes time difference. And that's the blue vertical line means that the peak of the observed position, and the red line means our estimate time if we use the gamma ray burst Lorentz violation scale as input to make estimation. And here, to our surprise, we notice that the energy difference between the first figure and the last figure is exactly what we predicted, the peak position. So from here, we can see that the Lorentz violation scale for the AGN case, if we compare the two peaks, and we make assumption that the time difference just due to light speed variation, we got this Lorentz violation scale. It's a surprise consistent with the Lorentz violation scale. We analyze the data from gamma ray burst. So it's another support. for the subluminal light speed variation, our previous conclusion from gamma burst. And also for this light curve from the another AGN. And from the previous one, it's no clear one-to-one correspondence between peaks. If we just compare the last two peaks, this low energy photon peak, this high energy photon peak, so their peak difference, the arrival time difference, just corresponding our supposed peak position for our suggested Lorentz violation scale. So we can think that our conclusion of light speed variation is also supported by data from AGN. It's not very strong support, but if we just compare the two cases, and we think it's a very big surprise because the peak position just corresponding to the red scale we suppose from Lorentz violation scale from gamma burst. So that's a two peak position. So we think our suggestion of light speed variation with the value we suggested is also supported by data from AGN, by light curve from AGN. And also recently, we make a theoretical study on the light speed from space-time form of string theory. So we found that our results from the data analysis is consistent with prediction of the speed, light speed variation from space-time form. So we published our results in this paper. And also in this paper, we noticed that the Lorentz violation features of photons, they have several different features. For example, is linear energy dependence of light speed variation. And also we mean that the prediction, the zero prediction is subluminal Lorentz violation. It means that the velocity of high energy photons is slower than low energy photons. And also in this theory, photons are stable, so no photon decay. And also no by refulgence effect for photon propagation vacuum. That's from the theory. That's also consistent with data observation. So the predictions for space-time form of string theory are consistent with all current observations, including our results of subluminal light speed variation. And another news is that we know that LHAASO is a very high energy detector in China. They use arrows to make detection of high energy photons. The energy can be as large as PeV scale. So it's a very big progress because previously people rare to make detection of TeV scale photon. But now LHAASO can make a detection of PeV scale photons. And the observation they make, they observed the highest energy photon observed by human being is 1.4 PeV. And this event gave a strong constraint on superluminal Lorentz violation, but it still gives a space for subluminal Lorentz violation. And also those observations are consistent with string theory model for space-time form. So we pointed this conclusion in this paper. The reason is that if there exists superluminal Lorentz violation, then photons, high energy photons, can have emission decay into electron-positron pairs. So if high energy photons are observed, it means that this decay process is not happen. So use that, we can make a very strong constraint. The observation of 1.4 PeV photon make a very strong constraint on the Lorentz violation scale of the superluminal case. So this, so we see here it's 5 orders larger than the Planck scale. So it means that the superluminal Lorentz violation of photons are very strong constrained by the LHAASO recent observation of PV scale photon. So that's our conclusion from this paper, and also similar conclusions in other papers. For example, the more detailed analysis by LHAASO of their data in this publication, and also by another group of Chinese group. And just 2 days ago, we published another paper, is a joint constraint on photon electron Lorentz violation parameter space. So the green one, I think the red one, the pink one is for constraint from photon. Then the green one is from the constraint from the LHAASO suggestion of 2.3 PeV electron. And the white space is a permission space for photon Lorentz violation scale. So here we found that our results permit the parameter space for new physics beyond relativity. And also our suggested subluminal Lorentz violation for photons is within this space. So it's also consistent with this constraint. So we think the last observation they gave the permission for subluminal Lorentz violation. Another point we need to study that is photon how to say suppression due to their interaction with the cosmic microwave background. We know that 2 photon, high energy photon can have interaction with the low energy photons in the cosmic background and produce electron-positron pairs. And the threshold for this to be happen is 400 TeV. So it means that photons with energy larger than 400 TeV should not be able to reach us if their distance are very far, because these high energy photons can interact with microwave cosmic background photons to become electron-positron pairs. So the high energy photon flux should be very highly suppressed. If we observe photons with energy larger than 400 TeV, it means that there may be some anomaly for this process. So that's we check this case. So the suppression of the of high energy photons in the universe propagation should be, if we reach 400 TeV, so we should not be able to see the high energy photon if they come to us with very far distance. So the LHAASO observation of 1.5 PeV, it means 1,400 TeV. So it's larger than this threshold. So the existence 1.4 PeV photon by LHAASO means something anomaly may happen to to this process. So we should check this process to see whether the threshold anomaly due to Lorentz violation. And from here, we notice that if ELV is less than this scale, the case 1, it means that this process cannot be happen. So the energy photon can be observed if they have energy larger than the threshold energy. They can still be observed because this process is forbidden due to Lorentz violation scale. And we notice that this scale is much larger than the Lorentz violation scale we suggested. So our case of the subluminal Lorentz violation is belong to the first case of this threshold anomaly. And if we make extension, this means the threshold anomaly of cosmic photons due to Lorentz violation can happen for above threshold photons to be observed. If we can observe any photons, they are from extragalactic sources, then we can consider such observation as signals for new physics beyond special relativity. So that's for CMB background. So we also make extension to the to the background of photons to the EBL case, extragalactic background light. And in this case, the density of this EBL light is not so big than CMB, but average energy is larger than CMB. So it have a lower threshold. So it means that the threshold is 260 GeV. So it means that if we can observe photons with energy larger than 300 GeV from a very far distance, it might be a signal for new physics beyond special relativity for this threshold anomaly to happen. So those picture and predictions are all consistent with string model of space-time form. So that's our conclusion about the photons. The energy cosmic photons provide opportunities to study the Lorentz violation of photons. So we suggest the subluminal light speed variation from analysis of gamma ray burst state with also support from AGNs. And the LHAASO observation of 1.4 PeV photon poses very strong constraint on superluminal Lorentz violation. And the subluminal Lorentz violation we suggested permits the above threshold photon events. For example, LHAASO events, and also the recent observation of 18 TeV events by LHAASO from the new gamma ray burst 2022 October 9th just happened 3 weeks ago. So our prediction of optical transparency of cosmic photons can be tested by LHAASO observation of any above threshold photons from extragalactic source. So actually, we think the LHAASO observation of these events actually predicted our prediction. And this page was finished almost, I think, 2 years ago. So I think this can be considered as a support our prediction of threshold anomaly. And the new observed gamma ray burst, they are triggered by Fermi and Swift. It's very bright gamma ray burst with very short distance. And the LHAASO observation with more than 5,000 high energy events with energies larger than 500 GeV, including photons with energy up to 18 TeV. So we think that's a very big event. It should be a signal for new physics if this observation of this energy can be confirmed. And also a Chinese group with satellite also observed the low energy peak of this gamma ray burst. This Chinese satellite group we called Herbers. And this gamma ray burst is very rare. From a theoretical expectation, it may happen one such event every 130 years. And assuming other case, it may only happen every 500 years. So it's very lucky the LHAASO observed this event, because when this gamma ray happened, the LHAASO satellites just face the space directly to this gamma ray burst. So if it was not so lucky, the gamma ray burst may be at another side of the Earth. So LHAASO may have the chance to completely cannot observe any event from this gamma ray burst. So this is a very good chance LHAASO make very good observation with very large data sets, and also including photons with energy up to 18 TeV. And so that's this gamma ray burst. And just, I think the second day after this observation, we released an archive paper on October 11 to show that this observation of this 18 TeV events are not expected from standard model of EBL, standard model special relativity, because here we see that it's very strong surprise. So there should be no chance to make the observation of this event. So we suggested that Lorentz invariance violation induced threshold anomaly can explain this event. So that's just in this preference, we suggested this. And also we make another analysis of the Fermi observation of 99 GeV events. So that's a peak, low energy peak by Fermi GBM, and the high energy events is observed by Fermi light. So the blue line, the dashed blue line is the real arrival time of these high energy events. And if we make assumption that this event is of the Lorentz variation scale, light speed variation scale, just from our previous analysis. So this red line, just corresponding to this peak, is the emission time at the source with this low energy photons. So this time we suggested that this Fermi light 99 GeV events was emitted at the source with those low energy photons at the same time. So we think this gives us strong support, but it's a supplement support. It's not direct support because you don't know what should be the exact emission time of these energy events. But here we just make our estimation and to compare the emission time with the low energy photon. We just found this peak is with the same emission time with this energy photon events at the source. And also from the Herbert's flat curve. So that's the emission time of this observed time of these energy events. And here we notice that they are just in the two deep regions of two peaks of low energy curves. So this seems unreasonable because this energy photon was very lonely from this curve. And if we draw our picture and we found that here, it just have a peak of low energy photon. And the peak is almost invisible because the detection ability of Herbert's is not so good as Fermi light. But here it still gives us that this energy events of Fermi just emitted at the same time with this low energy peak of the Herbert's light curve also. So we think this new observed gamma ray burst, these Fermi events, can be considered as a supplement support for light speed variation from our previous study. And also we published the paper because previously we think also axion photon oscillation with a connection with LHAASO observation of PV scale photon. And after the LHAASO released their new observation of this new gamma ray burst. So we also published, submitted a paper to make suggestion that the axion photon oscillation can serve as an alternative mechanism for the high future of this new observed gamma ray burst. This is just a suggestion. We think it's an alternative mechanism for the new physics from this new gamma ray burst. And also, we can make extension of our analysis from photons to cosmic neutrinos. So this is by Italian group. They reproduced our previous photon analysis, and then they make extension to neutrinos from the S-cube observation. The energy of the neutrinos with the energy up to a few hundred, from tens TeV to a few hundred TeV neutrino events. So that's S-cube observation. They make detection of neutrinos from the S and the South Pole. And the advantage is that the energy of the neutrinos very big, from TeV scale to even PV scale. So the time difference can be very large, can be a few hundred seconds to days, to hours, days, even weeks. And so the intrinsic time difference at the source emission of neutrinos and photons can be neglected. So from this analysis, we try to check the S-cube events with energy larger than 30 TeV, including also 4 events of PV scale. That's previous results by the Italian group. So we reanalyzed the data, and to our surprise, we found we can have also the neutrino events fall on the line. But we have earlier arrival time and later arrival time. And this line means that these neutrinos are observed later than the gamma ray burst photons. And this line, the lower line, the events on the lower line means that they arrive earlier than gamma ray burst. So what should be the reason? It has both signs with earlier arrival and later arrival photon neutrinos. But I thought of this problem. I think it's a surprise they fall on a straight line. So it's a surprise. And also, I thought that the S cube collaboration cannot make a distinction between neutrino and neutrino. If neutrinos and neutrinos, they have half-half probability. And if half of them are neutrinos, half of them are antineutrinos, they have different propagation property. So if one of them is superluminal, so the end particle is subluminal. So we can explain this picture. And also we checked not only the 4 events by the Italian group, that's a 4 event. This 9 events by the Italian group. Also, we checked the 4 PV events. And to our surprise, these 4 events can be also associated with gamma ray burst fall on a same straight line with the previous non-neutrino events with TV scale neutrinos. And so that's a detailed comparison with different gamma ray bursts, because we check the time difference of 2 weeks away from the observation of the gamma ray burst. And one interpretation of our results, it means that different properties between neutrinos and antineutrinos. So the velocity of, for example, of neutrinos and antineutrinos, one is superluminal, one is subluminal. So this figure just means that if they are true, they can be further confirmed. It means the CPT violation of neutrinos. It's a different property between neutrino and neutrino. And also we found from theory, for example, stem model extension theory, they make the right prediction neutrino and antineutrino should have CPT symmetry violation, this option. So in this picture, it means that the picture of both Lorentz violation and CPT violation of neutrinos and neutrinos is within the theory options. And also we check just PV S cube neutrino events. Previously, we just check very large from 16 TeV to 2 PV. But here we just, for the events around 1 TeV, just the S cube low energy neutrino events. And that's their data. And we check the data very carefully. We found the events from the north track, means from the ground. The neutrinos pass through the Earth. So it means that the down up neutrino events falls exactly on the same line as our TV and PV fitting results. It's within the region. So we draw this line, and we found another amount of north track TV scale events near TV. Gamma ray burst can be also associated with gamma ray burst, fall on the same line. So we found new support to the PV regularity from 12 S cube neutrino near 1 TeV. So that's 12 events near 1 T also support our conclusion. And we notice that near TeV events, a few tens, a few hundred TeV events, even PV events, fall on the same line. And the previous analyses are analyzed for S cube, we call track events. And then we analyzed also the shower events from the S cube. And we found that for the 24 neutrino shower events above 60 TeV, 12 events are associated with gamma burst. They can fall on the same line, but with very large error bars. And we notice several events, several shower events falls exactly on the same line as our previous. So we give additional support for both track events and shower events of S cube collaboration. They support the Lorentz violation of cosmic neutrinos and also support the TeV violation of neutrinos. And also just yesterday, I think today is published online, we published another paper to show that the string theory model of space-time form gives the support of Lorentz violation and also CPT violation of neutrinos, and consistent with our observation of the S cube results. So our conclusion for the ultra energy cosmic neutrino is that we associated S cube, TeV, and PV neutrino events with gamma ray burst. We found a regularity of these energetic neutrinos indicating Lorentz violation. So that's new physics beyond the relativity. And we suggested different propagation properties between neutrinos and neutrinos, indicating the CPT violation between neutrinos and neutrinos. Such a scenario from our data analysis we suggested is consistent with the string theory model of space-time form. So I finished my introduction of our works on cosmic photons and neutrinos and their relation with Lorentz violation.
Okay, we would like to thank speaker. We are a bit delayed, so is there any quick question?
I have one question.
Okay.
Yeah. So I mean, the question is whether the Lorentz violation scale, scale for photon and neutrino are the same.
They are of the same scale but different. The Lorentz violation scale for neutrinos is 2 times that of photon case. Almost 2 times.
So that means the slope is maybe different.
Their velocity are different. So it means that the Lorentz violation is more strong for photons than neutrinos. Because the Lorentz violation scale for photons is 1/2 of that of neutrinos.
But in the neutrino analysis, did you assume that almost massless approximation for the neutrino mass?
The neutrino mass is completely negligible. We make a calculation, estimation, because the energy is very large, TeV, PV. So the mass is completely negligible.
Okay, thank you. Thank you for very nice.
Yeah, thank you.
Yeah.
So, any first question?
No more question? Okay, if there is no more question, let's thank speaker again.
Yeah, thank you very much. Thank you very
And-
much.
Okay, let's finish the formal part of this seminar. And if you have a personal question, please remain here and ask him personally. Okay, let's finish the formal part.
Okay, okay,
yeah.
thank you.
Yeah, thank you. I mean, you did lots of work. Yeah. Okay, thank you. Actually, I mean, contact you again personally about your work. Yeah. Anyway, thank you very much for your nice talk again.
Yeah, thank you. Thank you
Yeah.
for invitation. Yeah, it's my pleasure to give a seminar to colleagues.
So, by the way, so when did you start this topic? Did you start it before opera experiment?
I think the first paper, 2008, I think.
So is it before the opera experiment?
I think the first paper probably. Yeah, here. Is 2009, and before that we started the GZK cutoff. So Lorentz violation can be related with the GZK cutoff, the cutoff of ultra high energy cosmic rays. But later on, because the cutoff was observed, so people use that give a very strong constraint of Lorentz violation of protons.
I mean, one simple question is that you now conclude that linear energy dependence maybe the
So
maybe,
from our side, we think we are making a suggestion.
right.
Yeah,
So,
we still need data to confirm it.
Right, but based on your analysis, it seems to be, quite plausible. But the question is that, generally you can consider linear and quadratic term as well. So can you, so if you have two term, can you constrain the coefficient from the data?
So actually, because for the quadratic case, we did not find a very strong regulation. And also the energy scale is around, I think it's very far from the Planck scale.
Right. So that was your point, right?
Yeah, so we think maybe if we have enough data, we can check that. But at the moment, we prefer the linear case. And also in our study, we found very strong regularity. So the regularity is so strong and so nice. Because here, just use trig time, we cannot find very nice regularity, but it still have a very strong regularity. And these points we can think fall on same line. But if we make the low energy light curve, the peak of the first significant peak as a low energy photon, so we arrive at this single regularity. So to our surprise, we thought that to be too good to be true. So we checked from various aspects, and we found another event support us. And also we checked from the general analysis, even from the early arrival high energy photons, the support. and also machine learning method. And also it's supported from the AGN, the peak position. And also recently, the new gamma ray burst, it can only serve as a supplement, not a strong conclusion, just a supplement. And also it's a good news that our suggestions are consistent with the theory prediction. So it means that all the features can be understood from theoretical frameworks.
Yeah, okay. Okay, thank you very much.
Yeah, thank you. Thank you.
Yeah, so let me, discuss again by email.
Okay. Okay.
Yeah, okay, thank you. Bye.
Thank you. Bye.
Bye.